6. There's our 6 carbons, and then here there's also 6 carbons. Over here we've got these 5 coming across here, and then there's that extra methyl group coming down off of the 2 the same way. So that's our first rule of line structures. If we want to talk about how you officially draw these things, is that we're going to assume carbon atoms at each end and vertex, vertex being like an intersection of 2 lines. So where 2 lines come together, or the bumps, that's where we're assuming that there are carbon atoms. So we're going to get rid of the carbon atoms within there. That also requires this kind of geometry, this kind of zigzag geometry. Because if we just used a straight line, if we used like this same kind of geometry, we wouldn't be able to tell how many carbons there were. It would just look like one big line. So we have to use that zigzagging. And that has the additional advantage of being a better way of modeling what the thing would actually look like. As we saw in those models last week, that's actually the structure of what these things look like. So we make those zigzags, and each time it zigs or zags, however you define that, that's going to be another carbon atom. How do we know how many hydrogen atoms we have then, if those aren't shown?
Doesn't it naturally add 2 extra hydrogens every time there's another carbon? So like if there's like 4 carbons, so it'll be like 6. There's 5, it'll be 8.
Kind of, yeah. But we have to be a little bit more specific than that, because like this carbon, for instance, has 1 hydrogen on it, whereas this one has 2, whereas this one has 3. What's different in those? Why do they have different numbers of hydrogens on them? And how does that translate to a structure like this? What do you think? Because you're right that there's kind of a rule, like an assumption about how many hydrogens there needs to be. How can we figure that out? Okay. Well, the way we figure it out is because we know that carbon has to have 4 bonds all the time. So if like this carbon in this line structure is shown as bonding to 3 other carbons, we know there must be 1 hydrogen there to fill the 4 bonds. This carbon is connected to 2 others, so we know there must be 2 hydrogens there to fill the 4 bonds to carbon. And then one on the end is only connected to 1 other carbon, so it must have 3 hydrogens to fill that 4 bonds that's required. So our next rule can be that we always assume enough hydrogens. And the real way to say it would be to fill carbon's valency, which is another way of saying get it 4 bonds. So we always assume that however many things a particular carbon is connected to, there's going to be enough other ones so that there's 4 bonds to that carbon total. And then our last rule is that other atoms that are not carbon and not hydrogen they don't get abbreviated. So we don't do anything to them. They stay the same. And I'll show you an example of that. Their attached hydrogens stay too. Let me show you what I mean by that. If we have something like that has this OH on the end, we can abbreviate the 3 carbons as carbons, but we don't abbreviate the oxygen or the hydrogen attached to the oxygen. So that becomes this. And so we don't cut that hydrogen off of that oxygen. We don't do anything to the oxygen. We leave that the same. The only things that these structures abbreviate are carbons and hydrogen. Carbons and the hydrogens connected to carbons. Okay, so let's try it. I'm going to draw a couple, well, I'm going to draw one condensed structure and ask you to draw a line structure, and then I'm going to draw a line structure and ask you to draw a condensed structure. I'll try to leave these rules up there. Okay, so here's a condensed structure. So you can draw that as a line structure. And here's a line structure. And see if you can draw that as a condensed structure. All right, so for the line structure, how did you draw that? Like, how did you go about it? What was your method? Because I haven't really said here's how you specifically should draw it.
Counted the carbon.
So you counted the carbons. How?
Counted the ones going across and made enough bumps for them, and then I drew lines down.
Okay, so let's try that. That's a good technique. So we and instead of just counting, sometimes it can be helpful to actually number them too, just to make sure you've got enough, especially in like the stress of a test or something like that. So we've got 5 carbons, which means we need 5 bumps going across. It doesn't matter if you start going up or you start going down. Which way did you do it? Did you start going from low to high or high to low? Anybody? You start high to low. Okay, so we'll go 1, 2, 3, 4, 5. Something like that. It's always helpful to number these also because it's easy to forget the ends. Remember, when you put your pencil down, that's 1. But sometimes we want to draw to 1 first, and that's not right because then you've got 2 of them there already. So make sure if you number them after you're done, you know to check. Then you can also, the numbering helps you to know which substituent goes on which carbon. If we look back at that condensed structure, you see a methyl group on 2 and 3. So we can put methyl groups on 2 and 3. Now, one thing I'm going to do a little bit differently on the structure is I'm going to put that methyl group up instead of down. Now, I could draw it like that. The reason that we put it up instead of down is part of what we do with these line structures is we want to approximate the bond angles, like what is the actual angle that these things take. And if you look at the way it's drawn right there, that's a very, very condensed bond angle. It's kind of crowded in there. And if we were to draw anything kind of on that, it would be kind of crowded in there. So we usually always go away to try to make that wider bond angle. And that's just a convention. If you drew it down, that wouldn't be wrong. But it just looks a little nicer if you do it this way. So yeah, that's what that particular line structure would look like for that structure. Okay, now what about drawing a condensed structure from a line structure? How did you go about that? Have a good way of doing that?
Count the bumps.
So again, you count the bumps, yeah. And actually, in this case, you can even go easier than counting the bumps. You just put a carbon at each position where there is a bump. You see what I'm saying with that? So let's try that. We just put draw the exact same structure as it is, except instead of making the lines meet, we put a carbon in there. So it's almost like we're stretching out everything to fit carbons in there. Like that. And then you can go back and add enough hydrogens to each carbon so that each carbon has 4 bonds. So like this carbon, how many hydrogens would we have to put there?
2.
2, yeah. And when it's convenient, you can write them right next to it. If it doesn't quite fit, you can write it below or above or to the left. It doesn't really matter as long as it's right by that carbon. So we can put 2 here and 2 here, 2 here and 2 there. Because each of those carbons is bound to 2 other carbons. So it means it needs 2 more to make 4 bonds total. Carbon always needs 4 bonds. So if it's connected to 2 carbons, then its other 2 bonds are the 2 hydrogens. So what about this one right here? How many hydrogens does it need?
1.
Right, just 1, because it already has 3 bonds. And then 2 here and 3 here. And so there's a condensed structure for that one. Notice nothing happens with the oxygen. It stays there. It doesn't get a hydrogen or anything like that. Okay, so we're going to start using these structures now, so you get used to them a little bit more as we talk about some of the other stuff we're going to look at today. So first, let's try to do a couple naming exercises using those line structures. Now you might want to get out your notes that had some of the names, the names for the chains and stuff. All right, here are 3 alkanes drawn this time in line structures. So see if you can come up with a name for each of those. Oh, sorry, I was going to, this is a little different. And then third, when you've done that, I'm also going to write down a couple names and see if you can draw line structures for these names.
Just a question.
Yeah.
The last one,
Mhm.
structure, did you mean to make that bottom line longer than the top one?
You mean this one?
Yeah.
No,
Okay.
it doesn't really matter. Yeah, they're about the same. Oh, I guess it doesn't. It doesn't look as much longer on my screen, but you're right, it is. Is that better?
I just didn't know if there was like a trick to it.
Oh, no. That's just how it is. Now this name here, I know this has something in it that we haven't dealt with before, but I figured you could probably figure it out. What do you think chloro means? If we have a chloro substituent instead of methyl or ethyl. What?
Chloride?
Yeah, right. All right, so you got three structures to name and 2 names to structure. I'm just going to look around and see. All right, who's got a name for this first one? You want to give it a try?
Three propylpentane.
3-propylpentane. Anybody else? Get something similar, different? Nothing? Still thinking about other ones? All right. Well, let's take a look at it. So the longest chain is 5. That leads to the pentane. Is that what other people found also? I think there's a longer chain.
Oh, yeah, there is.
There is, isn't there? Yeah. So the longest chain is this one. Which is 1, 2, 3, 4, 5, 6. And this is a common trap that you always see the chain going from left to right horizontally as the main chain that you first look at. And everybody does that. And remember that the rule is always the longest chain. So you got to find the longest one, even if it takes a little bit of a weird path. Got to find the longest one. So this should, better than 3-propylpentane, this one should be 3-ethylhexane. All right. What about this next one? No, nobody feels confident anymore. Say, this one's not. There's not really a trick here, but you do have to know how to name it.
1,3-diethylcyclohexane.
Yeah, you got it. 1,3-diethyl cyclohexane. So we recognize that there are 6 carbons around in this ring. You want to number it so that those substituents have the lowest possible numbers. You could either go this way or you could start down at the bottom and go counterclockwise. And then you come out with 1,3-diethyl cyclohexane. There's 2 ethyl groups. The ethyl groups are here and here, hanging off of the 1 and 3 carbons on the cyclohexane. Carbons 1 and 3 of the cyclohexane. Okay. And so what does that make this next one?
One, 2-dimethylcyclobutane.
Yeah, 1,2-dimethylcyclobutane. So again, when there's a ring, we use that as kind of the main name. The ring here has 4 carbons in it. That makes it a cyclobutane. And we've got methyl groups on the 1 and 2. So 1,2-dimethylcyclobutane. All right, and then drawing these next couple structures. Oops. Let's take a look at that. So for drawing the structure from the name, usually the best way to go about that is to find that main part of the name, the end of the name, that tells you what the longest chain is. In this case, that's cyclopentane. So we would draw a cyclopentane, which in a line structure is just a pentagon, 5 things around. And then we would number it somehow. And since you're drawing it from scratch, it doesn't matter how you number it. And then you need to put chloros, so Cl, on the 1 and 2. And that's true. That naming scheme, by the way, is general for all the halogens in that row. You can have fluoro, chloro, bromo, or iodo in your names. Now, if you're not comfortable just drawing the line structure like that, that's fine. You can draw it as a condensed structure first and then turn it into a line structure if that's what the question is asking for. So we'll try that with this next one, 2,2-dimethylbutane. The main chain is butane. So you might draw 4 carbons in a row for butane. And then 2,2-dimethyl tells you that there are 2 methyl groups and they're both on carbon 2. So 2,2-dimethyl, carbon 2, carbon 2. Now you can go ahead and fill that in as a condensed structure. If you want. Or you can go right to drawing it as a line structure. So you've got 4 carbons in a row. So you got to go 1, 2, 3, 4. And then 2 more carbons on number 2, which we kind of put like this to spread them out. If you put them straight up and straight down, that's okay. But usually you'll see it like this. That's what that line structure would look like.
Does it matter if you start your lines going up or down?
No. So you could draw it also like that. Yeah. Okay. Next, we're going to get away from the alkanes a little bit and go into another functional group called the alkenes, very similar. But first, we're going to look at one thing that applies to both of these. And that is saturated versus unsaturated hydrocarbons. So we'll often describe a molecule as being saturated or unsaturated. And by saturated, we mean, whoops, the most possible hydrogens. So if a molecule has the most possible hydrogens it can, we call it saturated. And let me show you what that means. If we take, let's say, 4 carbons, it doesn't matter how we arrange them, the most possible hydrogens that can be on there is always 10. That's C4H10, and that is saturated. You can't fit any more hydrogens in that molecule. You can't put them in between the carbons because hydrogen can only have 1 bond, and you can't put them anywhere around the outside because carbon can't have more than 4 bonds. So that's as many as could be there. But there are ways to have compounds that have 4 carbons but not 10 hydrogens, but fewer than 10 hydrogens. And that's what happens when we add something like, for instance, a double bond. So if we had the same type of structure, but those first 2 carbons had a double bond between them, that is, they shared 2 pair of electrons instead of just 1, now there's not room, so to speak, for as many hydrogens there. So like this one, it gets 2 hydrogens, and then that's it. That's as many bonds as it can have. That's 4 bonds. This one's now just going to get 1, because it still can only have 4 bonds. And these 2 are the same as before. So in this structure, each carbon still has 4 bonds, but now we have fewer hydrogens. So now for 4 carbons, we have 8 hydrogens instead of 10, and that's called unsaturated. There's one other way that you can have fewer than the maximum number of hydrogens, and that's if you connect things in a ring. So if we make a cyclobutane, and we add enough hydrogen so that each carbon has 4 bonds, we once again have fewer than 10 hydrogens, so we have C4H8 again. And that's also unsaturated. And so you could imagine if we compound these things, like we have multiple double bonds or a triple bond or a ring and a double bond, that kind of stuff, you can make it even more unsaturated. And this is where the term saturated and unsaturated fats comes from also. You've heard that. Saturated fats are these long molecules, usually 12 to 20 carbons, that have all hydrogens, so no double bonds in them at all. Unsaturated fats have double bonds, so they don't have as many hydrogens there. And so they look more like this. If you've heard of things like omega-3 fatty acids, that means omega is the end of the carbon chain. So that means 3 carbons from the end of the chain, there's a double bond. So that's where that terminology comes in. Because saturated fats are surrounded by hydrogen like this, they're long and straight chains, so they can pack together very tightly. And that's why saturated fats are often solids like butter or animal fat. Unsaturated fats with these double bonds in them tend to kink and kind of be crooked, like they'll go like this and then angle down this way, so they can't pack quite as closely, and that's why they're usually liquids. They don't have quite as strong of dispersion forces holding them together. So that's where that comes from. Excuse me. And this introduces the next functional group that we're going to talk about, which is alkenes. Alkenes are just double bonds. Before we had the alkanes, now we have the alkenes, so they only differ by a letter. But they differ greatly in their functionality. Alkenes are reactive. They can do all kinds of different reactions, whereas alkenes mostly don't, except for combustion and some other basic stuff. So we're going to talk about some reactions with alkenes tonight. Now, one thing to know about double bonds is that they can't rotate. When we talked about the alkanes before, we always said, okay, you got to be careful when you're naming them or when you're trying to see if they're the same or not, because they can just kind of rotate. And when we had the models, you could kind of stretch them out or flip them in different ways. And double bonds can't. So if you have, let's say, this molecule, and then this one, oops, sorry. Those both have a double bond in the middle, but they're very different structures. They're both a chain of 6 carbons with a double bond in the middle. But because this one has this kind of a geometry and this one has this kind of a geometry, those are going to be very different structures because they're kind of locked in that position. So they can't just, in this one, we can't just kind of flip it up to be the same like we could with the alkanes. It's stuck down like that. There are words for these. This one, where it kind of alternates like that, is called trans, and this one is called cis. But more importantly, that you just know that those can't rotate. The other thing we need to do with alkenes before we can talk about the reactions is talk about the names. Now, naming alkenes is pretty easy because the naming rules are basically the same. The only change is if we have a structure like this, instead of butane, we call that butene. So alkanes end in ane, alkenes end in ene. And then there's one other issue we have to deal with, And that's the fact that butene actually is not quite a general enough term. Because this molecule also has 4 carbons and a double bond. And so this one would also be a butene. Which means we have to be a little bit more specific. The way we're more specific is with a number. If we number this chain starting from one end, you'll notice that here on the one on the left, that this double bond starts at number 1, whereas over here, that double bond starts at number 2. So that's how we differentiate these two types of alkenes. This one's called 1-butene, and this one's called 2-butene. Right, just like with substituents, we put a number with a dash to show where the double bond is in the chain. We can also have substituents in alkenes as well. So we can have something like this. Oops. Put a line there. There. This one we would number starting over here. 1, 2, 3, 4. And we'd call this 2-methyl-2-butene. The substituent, the methyl group, is on carbon number 2, and the alkene, the butene, starts at carbon number 2. Now, something that hasn't come up in our examples yet is that when you're naming, the double bond gets the numbering priority. Right. So that means that if we revisit something from up here, or from before, this structure, we said that this was the longest chain. And so therefore, this becomes 3-ethylhexane. But now let's say instead we have this kind of a structure that has a double bond there. Actually, wait, that doesn't change our issue here. It's not a good example because we let me change this. This is not a good example. Let's say we did this. Yeah. Okay. So this one looks like it should go across again, but then when we look at it more closely, we see that this is actually the longest chain because that's 6 carbons. And if we start numbering from the bottom, making the substituent closest to 1, that's on the 3rd carbon, so that's 3-methylhexane. Okay. Now let me draw that again, but with the double bond. So now this time, I'm going to put the double bond right here. Let's say that that one is actually a double bond. Well, the double bond gets the priority, so you have to now count this as the main chain instead of that longer chain. Because if we made that longer chain like we did before, it wouldn't have the double bond in it. So now we have to number it like this and call this 2-ethyl-1-pentane. Because the double bond gets the priority as part of that main chain as number 1. All right, so that's the difference with the alkene, is that you have to kind of watch out for that. You can't just pick the longest chain. You have to pick the longest chain that also includes the double bond. Let me write that here. So pick the longest chain that includes the double bond. All right. Okay, try a couple here. My examples. All right, here are two nice alkenes for you to try to name. Let's see what you can do with those. When you think you have a name, turn to the person next to you or near you and see how your names match up. Have any names for these yet? They're a little tougher because the double bond is thrown in there, but the procedure is the same. You want to give one of these a try? Maybe? No? I feel we got close. Something? Yeah, go ahead.
1 propyl, 1 cycloheptane.
Yeah, let's see. So 1. You got it?
Yeah.
All right, what do you think? Would you get something similar, different?
Well, I actually have a question on the
Mhm.
one above it, that 2-ethyl 1-pentane, do you mean pentene?
Yes. Sorry.
Hexane next to it is right.
Right. So let's take a look at this. The main part of the name is going to be the ring again, and we want to number it so that the double bond is part of that chain, and also that the substituent. We can do that here, so we can make that 1. If we make that 1, this has to be 2, because the double bond has to go between 1 and 2, not 1 and 7. Oops. So 3, 4, 5, 6. There's 7 in that ring. That's hept. So this is going to be a cycloheptene. All right. And then the substituent here is 3 carbons, and that's propyl. That's going to be 1 propyl, 1 cycloheptene. That's good. All right. And this next one we can do together. How big is the longest chain? 6. Right. It's like this, right? 1, 2, 3, 4, 5, 6. Now we're okay because the double bond is part of that chain. And normally the double bond would get priority. So if whatever gets the double bond the lowest number, that's the way we have to go. In this case, it doesn't matter because the double bond's right in the middle. So that ends up being having a substituent on 2, a methyl. And so that becomes 2 methyl, 3 hexene. We're good? Okay. Okay. All right. So now that we know how to name alkanes, let's talk a little bit about what they do reactivity-wise. Because one of the whole ideas of organic chemistry, or the reason it's so useful, is you can take all this diversity of different kinds of molecules and you can put them together to build the exact molecule that you want. Now, almost like playing with models. It's not quite that easy, but knowing the different reactions, you can mix different compounds and you can make exactly what you want. So when you see a drug or something in the store or at the pharmacy with a particular structure, somebody figured out how to put a sequence of reactions together and make that exact molecule that does that exact thing. And that's the power of organic chemistry. So we're not going to go through all of this. Obviously, you can take many semesters of this if you're interested in it. In looking at it further, we're going to look at a couple of the major reactions of alkenes and kind of leave it at that. So mostly what alkenes do is, well, they do a lot of things, but what we're going to talk about is something called an addition reaction. If you remember, before we called them combination or composition reactions, but in organic chemistry they're called addition, just means adding things together. One way that we do that is we take an alkene, like, let's say this one, and I'm going to use a couple different colors here. So this would be ethene. And we react that with a hydrogen molecule. So a regular molecule of hydrogen, H2. The result of that, well, is nothing actually. But when this is done in the presence of a metal catalyst, like platinum, palladium, or nickel, those hydrogens can actually add to the alkene and make a product that looks like this. So those hydrogens have added to the molecule. And what started as the alkene ethene is now an alkane ethane. And this happens for all sorts of molecules, like, well, really any kind of alkene, at least for our purposes. So let's say we have some kind of thing like that, a methyl cyclohexene. And we react that with hydrogen in the presence of some nickel. That was one of the choices there. The product is the alkene. Or the alkane, sorry. And it's tempting to think of this as just making the alkene or the double bond disappear. And that's kind of true. But think about this. This carbon here has 4 bonds, right? 1, 2, 3, 4. So no hydrogens. But then over here, it has 3 bonds and 1 hydrogen. This carbon over here has 3 bonds and 1 hydrogen. And this one has 2 bonds and now 2 hydrogens. So we've added those 2 hydrogens on. We can take a look at this here. So there's a hydrogen here. That hydrogen is still there, but now this one has another one, and this one has one as well. So we've added hydrogens, 1 hydrogen on each side of that double bond, and that's called an addition reaction, or more specifically, a hydrogenation reaction. All right, so if you wanted a molecule like this, one thing you might do is a sequence of reactions to end up with something like this, and then your final step would be to hydrogenate that to make this. This is how we make artificially saturated fats. So if you ever see on ingredients hydrogenated something or other, like hydrogenated soybean oil or hydrogenated safflower oil, there's a bunch of different ones that they use. That's the same type of process. So you're hydrogenating it by adding hydrogens and turning what is comes from the plant as an unsaturated fat into a saturated fat. And that's what we call things like shortenings. Like if you've ever cooked with
Trans fats?
trans fats are related to this. So trans fats are what happens when something is partially hydrogenated. So you don't actually saturate the whole molecule, you saturate part of it and you end up kind of stretching it out. And that's a trans fat. But trans fats still have double bonds in them. They're just the trans double bonds instead of the cis double bonds. And they're not good for you. So we're pretty much getting rid of trans fats these days. They're not around so much anymore because they're essentially unnecessary. Trans fats come from a time when people were afraid of saturated fats. Everybody knew saturated fats are bad. You got to avoid saturated fats. They'll give you a heart attack. So if you had a trans fat, you could technically call that an unsaturated fat because it still had a double bond, but it's just as bad for you as a saturated fat. They also happen to have really good shelf life. So that's why things like Twinkies last forever. Like if you heard about that sort of saying. It's because of the trans fats that never go rancid like regular fats.
I actually think they made a law, like they can't have trans fats anymore, but I think technically, as long as you have like a half a gram of trans fats, they don't have to put it on the label.
That's correct. So you'll see sometimes on labels, like it'll say trans fat 0 grams. It's not really 0 grams, it just rounds to 0 grams because it's just under half a gram. So if you really want to know, you look in the ingredients. And if it says partially hydrogenated something, that's still trans fat. So, and it still does have to be in the ingredient list. It doesn't have to be in the nutrition facts, but it has to be in the ingredient list. But at that quantity, it's not as bad as when we used to eat them. Like all movie popcorn was just cooked in buckets of trans fats, and all French fries were cooked in buckets of trans fats and all that stuff, and that's changed. Now, like if you get things like Crisco or other kinds of shortenings, those are fully hydrogenated. So those take vegetable oils, which are liquid, obviously, hydrogenate them to make saturated fats, which are then dense and solid like shortening. So that's the same kind of a procedure that we use for small molecules, for organic molecules. Okay. And then the other addition molecule the other addition reaction we're going to look at is something called hydration. What do you think that means? If hydrogenation is adding hydrogen, what do you think hydration is adding? Water, yeah. Well, the way this works, same kind of thing. It's actually a very similar reaction, just with a different catalyst. We're going to add water. I'm going to draw water in kind of a weird way here. Again, a different color. Normally we would write H2O, of course. I'm going to write it as HOH. The reason is just to show kind of what it does. In the future, we'll always just write it as H2O. Instead of some kind of weird metal catalyst, this is done with an acid catalyst. And the way we usually express an acid catalyst, the way they do it in the book, is a hydrogen ion, so an H with a little plus. And we call that an acid catalyst. If you remember from a few chapters back, a catalyst is something that lowers the activation energy of a reaction or speeds it up. So this reaction would kind of have a high barrier of activation. When you add acid to it, a little bit of acid, the acid isn't actually used in the reaction, but it facilitates the reaction and makes the reaction happen faster with less activation energy. So when you do this, you get, very similar to before, you go from an alkene to an alkane, and you've added the water. The water adds across the double bond, so it adds the H to one side of the double bond, the OH to the other side of the double bond. And this type of a group, when you have an OH on a molecule, that is called an alcohol group or functional group. So any molecule with an OH in it is called an alcohol. And those are really important in our bodies because many of our biological molecules have OHs in them, and so these things can interact with them nicely or not so nicely, depending on what you want to do. If we want to look at this in terms of a line structure, if we take something like cyclohexene and add water with an acid catalyst, remember, we don't draw those hydrogens. So the hydrogen goes to one side, the OH goes to the other side. We don't see the hydrogen because it's a line structure, so all we see is that OH. Now, does it matter if I draw it there or if I draw it here? It doesn't. Those are the same. took one and you just kind of like flipped it over, you get the other one. So those are the same thing. Now let's talk about what this reaction does when it's not the same. I'm going to draw an alkene in a condensed structure again so we can see it more clearly. And I know normally we'd take a break now, but don't have that much more to go, so you want to just go for a little longer. All right. We have to get up and take a break. You do so. So let's look at the same thing. Now we actually have choices. Now both sides of the double bond are not the same. It's not symmetrical. So there are two possibilities. So let me draw both possibilities. We can put one of the hydrogens here and the OH over there, or like that. You see the difference in those two? And those are different molecules, right? Because in one case, the OH is in the middle of the chain, and the other case, the OH is on the end of the chain. So those are not the same. So we have to figure out which one is actually more favored. And this can be done experimentally and can be verified that, in fact, this is the one that is favored. And this one we don't see so much. So how do we remember that? Well, one way to remember it is you look at the hydrogen, and the hydrogen always wants to be with its friends. So the hydrogen goes to the carbon with more hydrogens. In other words, you look at this structure over here, and you say, okay, I know this is an addition reaction. We have to add the water to the double bond. This carbon has one H on it. This carbon has two H's on it. So therefore, the H from the H2O is going to go on this one, and that leaves the OH going in the middle. You see that, how that logic works itself out? All right, so let's try it in a line structure format. All right, so you might see a reaction like that. Hey. You might see a reaction that looks like that. And again, you're going to say to yourself, okay, I know the H goes to one side and the OH goes to the other side. So which one's going to go where based on that rule? We can talk about the top or the bottom carbon on the double bond. So which goes to the top carbon, the OH or the H? Why? So you're looking at this one. How many hydrogens are attached to this carbon? How many hydrogens? Try again. There's actually 0 hydrogens on this carbon because you've got 1, 2, 3, 4 bonds already there because the double bond counts as 2. So this carbon has no hydrogens on it. This one has how many? Well, it has 3 bonds to carbons, and so then 1 hydrogen. So this one has more hydrogens than this one. So that means the hydrogen goes down here, and the OH goes down there. But if we'll see this, you'll see there's actually a little bit clearer way to look at it when you have a line structure like this. Because the other way of saying the hydrogen goes to the carbon with more hydrogens is to say that the OH goes to the carbon with more carbons attached. So like this carbon has 3 carbons attached This one just has 2. And so the OH goes where there's already a lot of other connections. And that's sometimes easier to see when you're looking at the line structure. Let's try another one. All right, based on the one above, look at what's happening above and see if you can draw a structure for the product for this reaction. And if you got that, see if you can fill in this reaction the other way. Anybody think we got these? Maybe something? Well, where did you put the OH on this one? On the carbon on the left or on the right? What do you think? Left or right?
I would put it on the right.
Put it on the right? Why? Just random
Have
guess.
the most carbon.
Yeah, so it looks kind of like this one. It has the most other carbons attached. So we might put it right there. That's right.
And it doesn't matter if you like put it in the middle going up, right?
No, I'm just gonna put it wherever. This is where I put it is like kind of the most spaced out there, so but it doesn't matter as long as it's connected to the right things. It's fine. So then the next one is asking you what kind of a molecule do you start with if you want to make that alcohol product? So what do you start with if you want to make that kind of a product? What do you think? Maybe I want to describe it or give a name. Maybe it's something.
I don't know if it's right, but I drew the double bond coming off that line.
Like this?
Yeah.
Yeah, that works. There's actually another correct answer also. And that is to make the double bond in the ring somewhere. That would make the same kind of a product. See how it's similar to what we did up here? Either one works. You just got to make sure the OH is going on the more substituted carbon, the one that has the more other stuff coming off of it. Another way of thinking of that is what we did up here, that the hydrogen goes to the other side. So if the OH goes on this side, the H goes over here. Right there. And that's the addition of water. So these kinds of things, as you practice them, will make a little bit more sense, just like anything else. And then the naming especially just takes a lot of doing it again and again and seeing different examples. So there are lots of practice problems in your book, so please go through and name some molecules and then look at these reactions as well. So you're ready for the quiz and exam next week. Quiz on Monday. All right, the last part of this chapter is dealing with an interesting class of compounds called the aromatic compounds. Now, what do you think that means? If you had to take a guess there. What does aromatic mean? Smells. Yeah. Yeah, that's kind of where this comes from, that these things smell. Although now we know that there are many, many aromatic compounds, that is, things that smell that don't fit in this category. So when we say aromatic in chemistry, we're talking about a specific class of molecules that are ring-type structures with alternating double bonds. So things like this. You may have seen that kind of a structure in something before. This molecule is known as benzene. And it's important. It's an important structure because it's especially stable, incredibly stable. All those double bond reactions we just talked about don't actually work on these types of structures because that alternating double bond in a ring structure makes it especially stable. So that means that this is something that comes up in a lot of like biological molecules, a lot of environmental molecules. It's the byproduct of a lot of combustion, incomplete combustion, and it's the basis of a lot of problem molecules. So for instance, benzene by itself, like that molecule, it's a liquid. It's a really good solvent, dissolves things very easily. It's also a carcinogen. So we don't use it much anymore, but people who went to college like in the 70s would talk about how like at the end of the lab, there would be a big bucket of benzene and you just like wash your hands off in the benzene bucket on your way out of the lab every day, stuff like that. We wouldn't do that now because it's carcinogen. But we do use some varieties of benzene for things. There's a slightly there's a less harmful version of it that just by putting a methyl group on there, you change its chemistry. And this is known as toluene. If you've ever built like a little plastic model or used some kind of plastic glue or like, I think rubber cement also, that's that smell, that solvent that always has that kind of glue smell. People talk about like sniffing glue. That's what usually talk about. It's not a good idea to inhale that. It's not as dangerous as benzene, but it's still not good to get inside you there. Then some other things that use this type of a structure. If you take toluene and then you put these NO2 groups around it like that, you get what's called 2,4,6 trinitrotoluene, which is also abbreviated TNT. So that's dynamite. That's the stuff that blows up. So based on that same structure. And then if you start linking these things together, you get even bigger molecules with similar properties. If you link two of these things together like this, with again those alternating double bonds all the way around, you get a compound called naphthalene, which used to be used in something called mothballs. If you ever smelled mothballs, which were these literally just these balls that had naphthalene in them that would keep moths away because they didn't like the smell, so you could put them in your wool clothes and things like that to keep them away. That's also not great for you, so we don't use that much anymore. And then the bigger ones, which I don't even know the names of some of them, but as you start building these things up, these are the products of complete combustion, and these are incomplete combustion. They look kind of pretty. They have these honeycomb-like structures. Hang on, I got my double bonds all messed up here. Let's try this again. These types of molecules are the byproducts of smoke. And this is why things like, well, this is part of the reason why things like smoking cigarettes are bad for you, even eating smoked meats. We talked a little bit about that before, the thing that came out from the World Health Organization. When you smoke things, you have this incomplete combustion, and molecules like these and even bigger ones get in the either in the meats or you're inhaling them directly into your lungs, and those are known carcinogens. So those are produced just the byproduct of burning organic matters. Things like this, if you hook them together like this, and there are different chlorines on here, these are known as Polychlorinated Biphenyls, or PCBs, which is an environmental toxin that is still present in a lot of lakes, and a reason that you can't eat certain fish from certain places, and especially predatory fish, because these kinds of molecules can accumulate in the fish and then become dangerous to people who eat them. So if you fish in particular places, there's usually, the DNR usually puts out lists of like what fish are okay to eat or not, and then how many of each fish you can eat over like a week or a year or a lifetime, because you don't want to get too many of these types of molecules, which are released into the water from usually some kinds of big industrial plants that are working with these types of things. So that's the aromatic compounds. A lot of bad, obviously, but if you look at structures of medications, they will also have these types of structures in them. They're very important for interacting with proteins and that kind of stuff. So a big part of our body and what we do. Now, you don't need to know all those names. You should know the structure of benzene. For this chapter, make sure you look at, let's pull it up. right now. If you go into the organic chemistry chapter right here, oops, make this bigger so everybody can see. And we'll try to, all right, so you're writing formulas of isomers, formulas from names, names from formulas, from the condensed, the structural formulas, the saturated versus unsaturated ethane, some hydrogenation reactions and hydration reactions, which is what we just talked about, and then the benzene molecule and the aromatics. So everything you need to know for the quiz and the exam is there, and then the practice, as usual, is listed in your chapter. So please work through those problems to practice so you're ready. So we'll have a quiz on this stuff on Monday and exam Wednesday. Now we have a little extra time, obviously, but I don't want to go into a new chapter. So is there anything you want to do now? Look at some stuff. What? Yeah. They're all online too. So, anything that's particularly troubling. We'll have Monday also for a little review before the exam, but that's getting a little close. So make sure you're working on stuff this weekend.
There was something in the nuclear chemistry homework
Mhm.
about like, what was like pro-fission or something, or it's like 0, 1E and not, like I know beta is like 0, -1.
Oh,
But we didn't really.
positron?
Yeah,
Yeah, we don't really talk about positrons.
that was in the homework conversation.
Yeah, it's in the chapter. It's the same kind of thing. You just like add up the numbers, but you won't see it on the quiz or exam because we didn't do it. I'm not sure it's in there. Let's check on if it's in here.
Are we not doing the lab?
The nuclear lab, we're going to do it 2 weeks from Wednesday. It's the last day of class.
Oh.
We skipped over it because it's a lab that we can pretty easily do all together pretty quickly while we do the checkout, whereas the organic compound lab was like more of a traditional lab. So I wanted to make sure to get that one in first.
Oh.
And then we have the exam next week, and then the week after we'll do the nuclear.
For some reason I thought it was today. Okay.
Yeah, we would have just done it today, but we can't get in the lab because there's another class up there. So yeah. This one, let me see. Yeah, it says write balanced equations illustrating alpha and beta decay. It doesn't say positrons, so you can probably ignore that. I should take that out. Do you happen to remember which problem it was? I have it written down. Okay. We'll find it eventually.
There was a couple of them though.
Okay. Let's take those out. All right, other stuff want to go over.
I'm sorry, I don't know question.
Yeah.
So for the hydration,
Yeah.
you were saying how the hydrogen is attracted to more carbons.
Right.
So
To more hydrogens.
what?
The hydrogen goes to the one with more hydrogens on it. The OH goes to the one with more carbons.
Okay.
Sorry, did I just confuse you more?
Okay, so the H and the H2O is broken off, goes to the one with more hydrogens, the OH goes to the one with more carbons.
Right.
Okay.
I guess maybe we should write that right under here too. OH goes to the carbon connected to more carbons. A little clunky, but. Okay, feels okay about things? Work on those homework problems so you practice the naming. That'll be the naming. These reactions will be the main part of the quiz. And then the exam will really be pretty cumulative. So there will be the nuclear stuff and this stuff, but the last exam was like a couple weeks ago, so there isn't that much new stuff. So it'll be a lot of practice of the old stuff. Yeah.
I just want to say somebody picked up my stuff on accident last Wednesday, so if you see the name
Oh, yeah.
in your things, can you please return it to me?
Yeah, when we were going through all the stuff, although I know some people are missing, but when we were going through all the stuff last week, yeah, you had like a big pile of it, and then it was just all gone. Somebody must have like put their stack on it and grabbed them all. So look through your stuff and see if you have very good stuff.
The rest of the stuff?
I do, yeah. Do you want it?
Yeah, then we'll pick out the stuff that I didn't pick out last.
Okay, I got it upstairs, so you
Oh,
can come up
don't
with
worry
it.
about it.
Okay.
I'll just do it like Monday, Tuesday.
Okay, I'll have it next week too. I don't have it with me right
Yeah.
here. Let me close this one.